Okay, so welcome to the fifth experiment. This is going to be the lecture for the Charpy impact test. Okay, so what we're going to do in this lab is we're going to use this Charpy impact tester, where it's basically a hammer right here, and it's going to swing down, and it's going to hit a specimen that we have in the center of our test stand here, and it's going to fracture it. So the main goal is we're going to have three different metals. We're going to have 1018 steel, 4140 steel, and then 660 aluminum. So we're going to get those three different metals, and we're going to put them under different conditions for temperature. And then we would put them here on this stand, and we would basically fracture them. So what we have is this hammer again. This hammer would come down, it would hit the specimen, it would fracture it, and then on this dial here, it would tell us the energy that it took to fracture the specimen in terms of foot-pounds. Okay, so in this Excel sheet, this is just an Excel sheet from a past student. So I'm not going to give you this data, I'll give you some other data, but this is just to kind of give you an idea of what we're going to be doing. We're going to have all of these different conditions here, where we have liquid nitrogen, dry ice, ambient room temperature, an oven, and then boiling water. Okay, so for all these different conditions, we would have all of these different metals in those conditions, and then we would basically, for example, we would take it out of the oven, and as soon as we can, we'd put it back on the test stand, and then we would run the experiment and fracture it. And then what you'll see is you'll get all that data, and then you'll see that at these different temperatures, these materials, they can absorb more or less energy depending on the temperature that they were at. And then we'll also see some trends where you see for aluminum here, it's fracturing at the same kind of energy, pretty consistent for different temperatures. So for the liquid nitrogen, let's say, if we're looking at the aluminum, that was fracturing at an energy of, or it was absorbing an energy of 17 foot-pounds. And then when we went up to boiling water, it also fractured at an energy of 18.5 foot-pounds. So that difference in energy is pretty minimal. Well, if we look at, let's say, this 1018 steel, at the liquid nitrogen, that absorbed an energy of 2 foot-pounds. So you compare that to 17 foot-pounds, that's a really big difference there. And then if we go up to the boiling water for the 1018 steel, that absorbed an energy of 78 foot-pounds. That seems like there's an issue with this data collection here. They might have taken a while to put this specimen on the test stand. So if you look at this other group here, this fractured at 136 foot-pounds of energy. So again, if we're looking at, let's say, this graph here, this is for a different group. Aluminum stayed very consistent along our temperature increase for the amount of energy that it was absorbing. But if we look at the aluminum, we see at cold temperatures, it doesn't take much energy to fracture. But then once we start to increase that temperature, now it's going to take a lot of energy to fracture. Okay, so we're going to discuss the theory about all of these kind of concepts in more depth once we get to the lecture, but I just want to give you kind of idea of what this looks like right now. So I'll upload this video to Titanium, but we can take a quick look at it. This guy, he's going to fracture a test specimen here. So let's watch it.
And we'll see how much energy that bar will absorb upon impact.
Okay, so you see that once this hammer came down, in this case I forget which specimen or condition this was at, but it didn't take much force, or this specimen didn't absorb much energy at all before it fractured. And you'll see this specimen, it has this kind of notch in the middle, which basically is going to act as a stress concentration to allow this to fracture a bit easier. So it's set up on this test stand here, and then it's going to fracture. And then this guy, he'll show us the fracture appearance.
So here we have the result of the ductile sample, and you can see how the surface of the sample looks as though the sample has been ripped. And
okay, so this is a ductile sample, like he said. And because it was ductile, or a ductile fracture mode, which we'll talk about later on, this fracture appearance, it's going to be kind of stretched out, kind of jagged here. You see it's raised up along these edges here. It's not a clean cut. And later on, he's going to do another test for a brittle fracture mode, and then we'll compare that to this kind of fracture mode that we see here. Okay, so I'm going to fast forward this to the other one.
And we see that it absorbed around 28 foot-pounds of energy.
Okay, so this one also absorbed 28 foot-pounds of energy. Okay, so now let's go to the next one.
So this is our brittle form of the metal. Here we have an example of a...
Okay, so I think the test specimen was aluminum, but they were under different heat treating properties, I think, or conditions. So this one was brittle, and if we look at his little dial here, we can see that this fractured at about, or it absorbed about 2 foot-pounds of energy. So this is a brittle fracture mode. And you can see that it's a really smooth surface here. So he'll talk about this for a moment.
Brittle failure. And you can see how the failure surface looks is nice and flat, like it's almost been cut with a knife. And you notice that it has absorbed a lot less energy. So we're reading around 2 foot-pounds of energy absorbed. This is not how we want our metal to perform. We want the metal to absorb a lot of energy before it actually fails. And
okay, so I'll also go to some pictures here. This is from my past semester's class. So this one right here, this is for aluminum, and this is when it was under a condition of boiling water. So if we look at this fracture appearance from this picture that my students took, we can see that, you know, it's pretty rough here. It's pretty jagged. Now let's compare this to, this is the same sample. It's the blue aluminum. Or is it steel? It's steel, sorry. It's 1018 steel. So this is for the liquid nitrogen condition, and we see that it's a lot more smooth in this area here. And up here, this kind of looks like a ductile failure, so they might have not set up the specimen quite correctly. Really, it should, look something a little more smooth like this guy had here. Maybe not quite as smooth, but it should be similar to that. And then this is just another picture. This was for the red sample, so the other steel specimen. This is under liquid nitrogen as well. And you see here we have all these ice crystals here. That was just because they didn't wait long enough to have this kind of evaporate off, but kind of looks cool. So the red steel, it was also fracturing or absorbing the same amount of energy as the 1018 steel. So it should have a similar fracture appearance as this sample here. Although again, we should see a more clean cut surface here. And I'll be supplying you with photos from another data set as well. Okay, so we got this kind of introductory part out of the way, so I just wanted to show you guys this before we actually get into the lecture, so you kind of have an idea of what we're going to do in the lab. So hopefully that helped, and now we'll start the lecture. Okay, so one of the main differences for this experiment versus all of the others that we have done so far is, in this case, we're going to rapidly increase our load, where we're going to have a very high strain rate, and that will cause our fracture. So in the past experiments, we've kind of increased the load gradually. If we think about the tension test that we've done, some of these loads, they took about 5 minutes depending on the material, like it is if it was aluminum. In this case, instead of having a load being applied over the course of 5 minutes till fracture, we're having an essentially instantaneous load to fracture scenario. So because of that, we're going to have very high strain rates as compared to the other labs. Okay, so what I've written out here is that, as we talked about before, our test specimen is going to absorb energy, and then it's going to fracture. And basically, this energy that is absorbed, it's called the impact toughness. So if we were going to plot our stress strain graph, the impact toughness is going to be the area under the curve for this graph that we would plot. We're not going to do this in this experiment, but it is something that's good to know. So if we look at this graph, and we're looking at this pink specimen here, this polymer that's not reinforced, basically, we see that because it's a polymer, it's going to have a lot of strain, but it's not going to be able to take a lot of stress. So even though there's a lot of strain, because there's not a lot of stress, that area under the curve, it's really not that big. So we can kind of think of that if we're thinking about metal, kind of like the aluminum specimen in our first experiment. For that, we saw that it had a lot of strain, but it wasn't able to take as much stress as the other steel specimens that we tested. And then if you look at this ceramic here, you think of ceramics, or you can think of like glass. It might be able to take more stress, but it's not going to go under much strain at all because it's brittle. So because of that, again, we don't have that much area under the curve, so it's not going to be that tough. Now here in green, we see that the area under the curve is quite large. So we are having a good amount of strain here, and we're also having a good amount of stress here that it can endure before it fractures. So in this case, it's kind of, I guess, a jack of all these two trades in this scenario, but it's not really a master of either. It's not going under the largest amount of strain, and it's not going under the largest amount of stress. However, if you have a metal that is kind of in this area, you can do some different heat treatments before you test your metal, and then you might be able to improve some of these properties. We're not going to test any of these special treatments that are done in this experiment, but again, it's something that's kind of good to know. Okay, so the next thing we're going to talk about here is brittle and ductile materials, and then we're going to kind of compare that to fracture modes. Okay, so I at first copied my notes down wrong, but anyways, we have two different kinds of material that we're kind of used to thinking about in our day-to-day life. We have brittle material, and we have a ductile material. So brittle materials, they're going to fracture with little to no plastic deformation, and they're going to have low energy on impact. So we know this from our day-to-day experience. If you have your phone, and you drop your phone, and you don't have a screen protector on there, well, you're going to shatter the glass on your phone. Even if you drop it, from 2 feet off the ground, it's still going to happen. I'm sure it's happened to a lot of you in the class. I know for my phone right now, I have a glass screen protector, and I kind of have that kind of shattered here, and I still haven't gotten that fixed. Anyway, so we have that. Brittle materials, they're going to fracture under a low amount of stress on them. They're not going to be able to absorb much energy on impact. Okay, then we have ductile materials. So for that, they are going to have plastic deformation before they fracture. So kind of an extreme here, but if we think about gum, that's going to have a lot of strain once we pull that apart. It's going to stretch quite a lot, and then at some point then it will fracture or basically, break apart. Okay, so we have these two different classifications here. However, this is a little misleading because these different materials, they might act in different ways under different temperature scenarios. So if I have, let's say, a ductile material, it might be ductile at room temperature, but if I put it at a temperature that's very low, like if we have liquid nitrogen, then in that case, it might not act ductile anymore. It might start to act brittle, where it would not take much energy to fracture at all. So while we think about these materials in kind of our day-to-day lives as brittle and ductile, we need to kind of make this distinction where these materials, they might act in a different characteristic way depending on the temperature that they're under. Okay, so we already kind of briefly talked about this, but again, we need to be more specific in our idea of brittle and ductile. So we're going to talk about fracture modes, where we can have a brittle fracture mode where the specimen is going to show little to no deformation until it fractures. Then we have the ductile fracture mode where the specimen is going to deform and then it's going to fracture. And as we noted before, we can have a material that's going to fracture, or it can fracture in either mode depending on some factors. In this case, for this experiment, we're going to be looking at temperature, depending on what temperature that material is currently experiencing. Okay, so we have an example of fracture modes right now. Maybe kind of a morbid example here, but I got this from Dr. James. So we have the Titanic, which is made of ductile steel, but as we know, the ship hit an iceberg and then the ship split into two. So that's showing that this underwent a brittle fracture. So why did this happen? The ship was in very cold water. Obviously, it was around icebergs. So this cold temperature that the steel was in, it kind of changed its material properties to where it is going to act as a brittle material, even though it was made of, as we would typically think of it, ductile steel. So the fracture mode that it went under was a brittle fracture mode because it split into two. Okay, so what we can do here is we can now talk about steel and aluminum, how they kind of differ. So we have steel. So when steel is hot, it's going to behave as a ductile material. And when it's cold, as we just kind of mentioned, it's going to act more brittle. Okay, and then we have aluminum. When that is hot, it's going to be ductile, and when it's cold, it's still going to be pretty ductile. So we will see this in the lab report for these two different types of metal here. And we'll see that in our ductile to brittle transition temperature graph that we're going to make. Those graphs, you kind of already saw that in the beginning of this lecture from the Excel sheet from one of my previous students. So we're going to talk about the idea of this graph, and then we'll talk about fracture appearance in a little more depth, and then that'll be it for this lecture. Okay, so we have the ductile to brittle transition temperature, or DBTT for short. So if we define this, this is going to be the temperature for which the impact energy is halfway between the impact energy for the highest temperature and the impact energy for the lowest temperature. So if you look at this graph, and we kind of think about this in the context of our lab as well, we're going to have one specimen here. For simplicity's sake, let's just imagine that this is some kind of steel here. So we're going to start out at a cold temperature. Okay, so let's say that we're like liquid nitrogen. Okay, so we'll see that that point right there is liquid nitrogen. So our temperature is going to be very low. And then kind of like we talked about earlier on, for steel, it's at cold temperatures, it's going to behave in a brittle fashion. So because of this, at this low temperature here, as we can see on this axis, because of that, it's going to be at a low impact energy. It's not going to be able to absorb much energy at fracture. And then we can see that on this axis right here that it's quite low. As we start to increase our temperature for this steel, it's going to start to behave more and more ductile. Now at this point, or in this range up here, let's say that this is boiling water. So in this case, the temperature is quite high. It's going to be the highest that we have for the lab. Yeah, it should be the highest. Okay, so for the oven, I'm looking at data right now from Excel. For the oven, it looks like that's going to be about 150 degrees Fahrenheit. And then, so the oven, that's going to be at 210. Really should be 212, but it'll be at 210. Okay, so in that case, our temperature is the highest that it's going to be for the lab. So that's why we're way over here on the right. And because it's steel, as we increase this temperature, again, it's going to behave more ductile. And because of that, it's going to absorb more energy on impact. So because of that, we're way up here as compared to way down here when we were at a low temperature. And now this ductile to brittle transition temperature, it's a little more mathematical and definition here, because we have this range here where we're kind of in between brittle and ductile. We kind of have a combination of each of these. Maybe in this case we're more ductile, but in this case we're also more brittle, but we're not just brittle and we're not just ductile. So that's why we're going to take this basically this halfway point for the impact energy. So again, it's the impact energy that's halfway between the impact energy for the highest temperature and the impact energy for the lowest temperature. Okay, so to find that, pretty simple here, but we're going to do DBTT is equal to the high temperature plus the low temperature divided by 2. So we're just going to take that average there, okay? And this is something that you're going to find in the lab. You're going to solve for that. Okay, so we already kind of talked about this first point, but not all materials are going to have this kind of defined slope or angle that we have for this impact energy. So in this example here, that slope, that's a pretty steep slope, so our transition temperature is going to be pretty well defined. But if we have a slope, that's like this in purple, this transition temperature, while it might mathematically be in the middle there, that range and the impact energy is not very large, but the range in the temperature is really large. Okay, so that's just something to keep in mind. So the aluminum, that's not going to have a very well-defined transition temperature because of that very minimal range in the impact energy. Okay, so in those kind of cases, and we've said this before, but the fracture might be kind of a combo of ductile or brittle. It's probably not going to be well-defined for being just brittle or just ductile. It's going to be kind of a combination of the two. However, if we do have a material that has a well-defined transition temperature, just like we have in this picture, you want to have the service temperature higher than the transition temperature so we can avoid fracture when in use. So we want to make sure that we're above this temperature where we're going to have a material that's defined in the brittle fracture mode. We don't want to behave like that when we're actually using this material in use. We want to make sure that it's ductile, so it's going to take a lot of energy to fracture when we're using this material. Okay, so the last thing would have been just to talk about the fracture appearance. But again, we talked about that earlier on, and we showed examples in the pictures. But to reiterate, if you have a ductile fracture mode, you're gonna have kind of jagged edges. It's not going to be smooth. It's going to kind of look like the material was pulled, and that's because it's absorbing more energy. So it takes a longer time to fracture, essentially, because it's going under more strain. This is, again, compared to the earlier labs like Lab 1 and Lab 2 when we did the tension test, those strain rates were very slow compared to what we're doing in this lab. Either way, the ductile strain rate for this lab is still going to be longer than the strain rate for the brittle materials. That is, that it's going to take longer to fracture for a ductile material than a brittle material. And then, so what you'll see for a brittle material, or a brittle fracture mode, I should say, is that you're going to have a flat plane, and the surface is going to be very smooth. That's because it's just, an almost instantaneous fracture. It's just our hammer's going to hit that specimen, and it's going to shear it into two. Okay, so if you have any questions for this lab or this experiment, feel free to reach out to me, either through email, or we can set up a meeting in Zoom or something like that. Okay, so hopefully you enjoyed this lecture. Again, watch the video that I showed in the beginning of the lecture. I think it's pretty helpful to kind of get an idea of what we're going to do in this lab. Alright, so hopefully all your studies are going well, and I'll see you all next time.